For problem 6.17, we're going to focus on carbocation, and specifically, we're going to focus on our process of determining if they are likely to rearrange. So first, we'll consider what type of carbocation we have. So in example A here, we have a secondary carbocation, and we see that on the carbon here to the right, we have a methyl group and also a hydrogen. So if this hydrogen was to migrate over here, we would end up with a tertiary carbocation. So I'll draw that over here, right? So this site here would be positive, right? So where that hydrogen has left, so positive site here. Then we see in B that we already have a tertiary carbocation, so it would not become more stable through any type of rearrangement. It could not become any more stable. So this one, we don't have to draw a resulting carbocation that's more stable. In example C here, well, we already have a tertiary carbocation, but you can see that through um, rearrangement of a methyl group, we could result in a another type of carbocation, a tertiary carbocation that is what's called allylic, or next to this double bond here. So what I'll do, for example, C, is I'll redraw the structure here. So we have our carbocation, we have two methyl groups here, a methyl group there. Okay, so this is our tertiary carbocation, and what can result here is a methyl shift. So this methyl group here will shift over, and we will end up with a tertiary carbocation here, but let's take a look at what happens. We have our structure here, and we have now, right, our double bond still there, and now our cationic site is here, and now there's two methyl groups up here. So this is after that rearrangement, what we would see, and there's actually a resonance stabilization that can occur. So that tertiary carbocation can actually become slightly more stable in this specific case, where we have this resonance stabilization that can occur. So this is one of the rare cases that you will see a tertiary carbocation rearrangement happen, only if it would become this allylic carbocation, which is stabilized through resonance. Okay, so let's take a look at example D here. And this is a secondary carbocation, but there's no way for a rearrangement to occur. So even if one of these, hydrogens was to perform a hydride shift, we would still have a secondary carbocation on any of these carbons. So if we had any type of hydride shift. So that rearrangement cannot occur. Let's look at example E here. And we have a carbocation, which is secondary. And over here, we have a hydrogen that can do a hydride shift. And we would result with this compound here, which will be a tertiary carbocation. So, right, we have secondary to tertiary over there. With example F, we could have this secondary carbocation have a methyl shift, and our result would be a tertiary carbocation once again. So that could look like this here. So there's our tertiary carbocation that will result for F. After that methyl shift. And let's take a look at G here. So we have a primary carbocation, right? This is primary, right? This carbon, that's the cation, is only bonded to one other carbon. So in this case, we could do a hydride shift, which could result in the structure down here. Right, so we have, let's draw it the same way, right? So we have this site here. So this would be a secondary but resonance stabled carbocation. And in chapter 7, we'll dive a little deeper into that, into what's called a benzylic carbocation. All right, and let's look at our last example here. So this is a tertiary carbocation already, and it is specifically a benzylic carbocation, right? So it's the same as what would occur in example G. So this will not have a rearrangement because it's already as stable as it can be. So that's everything for example 6.17. We'll continue with 6.18 in the next video.